Okay. Have you pressed the button?
Yes.
Thank you very much for coming to this evening event, the Lever-Hume lecture, I can never pronounce that, as well as the public event of the International Center for Mathematical Sciences. My name is Min-Young Kim, I'm the director of the ICMS, and it's a real pleasure to introduce tonight's speaker, John Baez. I haven't prepared anything as a speech. I'm terrible at giving speeches, but that, in this case, it doesn't matter at all because I could go on all night about John and his wonderful qualities without preparing anything at all. In particular, besides being an extremely distinguished scientist, well, I mean, I could go on about that as well because, you know, he's essentially founded a whole way of looking at quantum field theory, which is sort of the fundamental theory of the way things are made up, and everybody is working on ideas that stem from John's hypotheses or his conjectures from around 20 years ago, I guess, maybe, or even longer ago, right? So this is almost the most important area of quantum field theory, I would say, these days. So that sort of gives you a little flavor of the kind of science that he's been responsible for in his life. But most of the non-scientists know him as a wonderful communicator of science. He is literally a walking Wikipedia, except he's much more reliable than Wikipedia. And some of you may know that I dabble in physics sometimes myself, and anything I know I've learned from John over the last 30 or 35 years or so. So of course, as a result, I guess what I'm trying to say is that if you have any questions during this talk, please speak up and he'll go on and tell you everything more than you needed to know with whatever intention they started on. In particular, it's going to be I'm really looking forward to the topic of today's lecture, life's struggle to survive. I'm always struggling to survive myself. But obviously, what he's going to talk about is much more important stuff than my struggles. It's about the struggle to survive in the history of life on Earth. Is that right?
Yep, that's it.
Yeah. What it says, the lessons it has to teach us about our future. So I hope you'll join me in welcoming John to speak about this important topic.
Great, thanks. I'm not a walking Wikipedia, so. But anyway, it's a great pleasure to be invited here to speak about a topic that's near to my heart. So. Around 2010, I became very interested and concerned about global warming and started trying to learn climate science and learn paleontology a little bit, which is connected to that. And now I think everybody is practically somewhat concerned with climate science. But it's really interesting to me to see how the current day concerns about our changing climate and how it may affect our civilization, how they fit into the broader scope of the history of life. And so that's what I'm going to try to say a little bit about. It's not marching forward the way it should. I don't know. Something not working. Great. More of life's struggle to survive.
Let me see if Alex is outside. Oh, Alex? We seem to be having trouble with the slides. Do you know that? The slides don't seem to be moving forward. Sorry about that. Our equipment upstairs is much better.
So, life's struggle to survive. There you go. We're even now still struggling. So, we're in a very unusual epoch. We've left the period called the Holocene, which is a funny geological period whose name meant the present, basically. And we've entered a new epoch called the Anthropocene, which is different in that the biosphere is very rapidly changing due to human activities. The geologists are attempting to date the beginning of the Anthropocene, and of course it's a fuzzy issue, but we're in it now.
Sorry for the further interruption. We're not sharing the screen.
So you can get a glimpse of what's going on just from this simple graph of the Earth's human population in billions. And to a first approximation, you could say that the population was 0 until about 2000, and then it became infinite. That's a rough approximation, but you can see that it's basically flat, and then it's basically vertical. Now, some people seeing this graph think that the answer to all the problems I'm going to pose is controlling population, but I wouldn't say that's really the moral of this. In fact, one interesting piece of news is that the rate of population increase now is slowing down. The population is still increasing, but the population rate of increase percentage-wise is slowing down, and you may have even read newspaper stories about how China is worried that they won't have enough people and so on, which I think is not anything too much to worry about really, but this trend will not continue, obviously. But what it means is that everything that people do has been increasing. And one of the things that we do is we burn stuff. Our civilization is powered by burning first wood and then digging up coal and oil and burning it. And so we're putting out lots of carbon dioxide into the atmosphere. And that's basically what this is a graph of. So what's this going on? What's going on here? So this goes to 800,000 years ago, which is not that long ago in the grand scheme of things. And in this current era of the last 800,000 years, we've had ice age cycles. And when it's warm, when there's a lot of carbon dioxide in the air, so this is a graph of how much carbon dioxide there is in the air, and it's colder when there's less. And it's a feedback loop. When it's warmer, it turns out that more carbon dioxide leaves the ocean, and then that makes there be more carbon dioxide in the air. And when there's a lot of carbon dioxide in the air, it helps trap heat, and then it makes it warmer. So it's a very complicated cycle that could be very interesting to talk about. But basically, it's been wiggling back and forth due to the variations in the Earth's orbit, ultimately, until around now, when it shot up, and we are now in some completely new climate regime. And you can zoom in here and see that basically, starting around 1750, when we began the Industrial Revolution, we started burning a lot more stuff, first wood, then coal, then oil, then natural gas. And so the concentration of carbon dioxide in the air shot up, and it's going approximately straight up by geological standards. So what it means is that we have left the present, if the present means the era during which humans evolved, and we're entering some new climate situation that we are just beginning to see the tip of so far, and will continue to change rapidly within all of our lives here. So you've no doubt noticed the crazy weather events that have happened this summer, and you can see it here. This is a worldwide average of the Earth's temperature. It's a graph going from January to December of each year, and so like the bottom you have like 1850 to 1890, those blue curves, and then with each successive year it's been on average getting hotter and hotter and hotter. But this particular year has been a real exception. You can see the black line up there is 2023. You can see it shot way up above all the previous ones. A lot of that is due to the El Nino, which we're currently experiencing, which tends to make weather hotter throughout much of the Earth. But that's not, of course, the whole explanation. It's on top of the increase in carbon dioxide in the air, which is heating up the Earth. So you can see from this that the things are changing very rapidly, and we're not succeeding in slowing that down yet. And we're not just changing the weather now, we're going to change it into the far future, because once carbon dioxide enters the atmosphere, it stays there for hundreds or up to, say, thousands of years. So when you put in a lump of carbon dioxide in the air, 100% of it is there at first, and as time goes on, it slowly goes away in various ways, ultimately going down into the ground. For a while it goes into the ocean, but there's a limit to how much the ocean can hold. And so So if you wait for 100 years, 40% of it will be left in the air. If you wait 1,000 years, we expect that about 22% will still be left. And if you wait 10,000 years, well, then maybe something like 10% is left. So what we're doing now will have effects that resonate throughout the history of the Earth for at least thousands of years. And once it's in there, once the carbon dioxide is in the atmosphere, it's very hard to get it back out. People have dreamt up machines that would suck carbon dioxide out of the air, but you just have to ask people, okay, so what are you going to do to power those machines? And then they realize that it's sort of a ridiculous idea because, well, right now we'd be powering them by burning carbon. And if you could power them with solar energy, then you should just use that solar energy to replace the burning of carbon. Now, maybe ultimately we'll develop a workable civilization based on solar and wind and nuclear energy so that we'd have spare energy that we could use to suck carbon dioxide out of the atmosphere. But we're nowhere near that point yet. The machines that we built for that purpose are just ludicrously tiny. So basically, this is like a temporarily irreversible decision that we're making to heat up the future. And if the Earth warms 2 degrees Celsius, which it seems like we're well on our way toward, in the long run, sea levels may rise about 10 meters over the next 10,000 years, which would be enough to drown most of our biggest cities. Although I carefully checked in Edinburgh, I think up here anyway, we're doing pretty well. That's why I like it here. One of the reasons. So the rise of sea level increase is very slow, and that is not the thing we have to worry about in our lifetimes primarily. There are other effects of climate change that you know, cities burning down and such, that will happen much faster, crop failures and so on. But this is the long-term future that we're establishing for ourselves. We're going to drown all the coastal cities that are really near sea level. But the important thing to realize that people don't necessarily realize as much is that the Anthropocene is about a lot more than just global warming. Because it's part of a big complex of things that we're doing. So for starters, the rate of species going extinct is somewhere between 100 and 1,000 times the usual background rate. By the way, if you grab a hold of my slides, you can click on numbers here and find links to them for sources. And you can see that, for example, in the case of fish, populations of large ocean fish have declined 90% since 1950, which is an amazing change. And if you look at how many animals there are, if you count them by weight, count them by biomass, right now 96% of mammals are either humans or livestock. So only 4% of animals remaining on the Earth are wild by now. So we've basically completely taken over the biosphere as far as animals or mammals go. I should say that there are lots of ants. Okay, so I'm here. I'm just talking about mammals. If you counted ants and other things, it would not seem so bleak. About 1/4 of the chemical energy produced by plants, right? Plants convert solar energy into chemical energy, but about 1/4 of all of that energy worldwide is now being harnessed by humans. And we're tapping into other aspects of the biosphere. So we now take more nitrogen out of the atmosphere and turn it into nitrates for the purposes of deliberately making fertilizer through the Haber process than all of the natural processes combined, like plants fixing nitrogen. And 8 to 9 times as much phosphorus is flowing into the oceans than the natural background rate, because for fertilizer you need phosphorus, and we're digging up lots of phosphates, fertilizing plants with it, but we're not terribly good at keeping the fertilizer in the ground, so rainwater washes it down, you get rivers full of phosphates, and then you get these dead zones in oceans near the river estuaries. So you see that we've really transformed the whole biosphere, and I'm not saying that transforming the whole biosphere is necessarily a bad thing, but we're doing it in a very oblivious manner where we just haven't been really thinking about what we're doing. But, so that may seem fairly bleak, and I think it is, to be honest, but it's good to know that our crisis, the one we're facing now, is far from the first that our planet has seen. So I want to say a little bit about other events that life has gone through during the history of the planet to set our current crisis in some perspective. So a really interesting one happened somewhere between 2.7 and 2.3 billion years ago, and that's when photosynthesis first arose, when plants, or algae actually, first started learning the trick of converting sunlight into energy, but in the process, turning carbon dioxide and water into useful chemicals useful to them, but then also this waste gas called oxygen, which was completely useless to the organisms at the time, and is also incredibly chemically reactive, much more reactive in certain ways than the methane and carbon dioxide and nitrogen that were in the atmosphere at the time. So this is a deadly substance. There are lots of bacteria even today that can't survive in the presence of oxygen. And at the time, no organisms had defenses against this poisonous gas. The oxygen collected and formed these banded iron formations. Basically, iron was oxidizing and forming these layers, and we see evidence of that from this time period or later. So at first, the oxygen, which was poisonous, was being absorbed by iron and organic matter that was sitting around. It hadn't oxidized because there hadn't been oxygen yet. But eventually that reservoir sort of got used up. There was too much, so concentrations of oxygen in the air shot up. This is a rough sketch from 3.8 billion years ago to now of the concentration of oxygen in the Earth's atmosphere. And so it sort of started slowly creeping up and then faster. And no one has any real fossil records from so long ago, unfortunately, but we could guess that perhaps most of life on Earth might have died from oxygen poisoning at this time, and it's called the oxygen catastrophe. So now we're having a carbon dioxide crisis, but then we are having an oxygen catastrophe. And as oxygen entered the atmosphere, methane, which was very concentrated in the Earth's atmosphere, was eliminated because it reacts with oxygen. Methane is a powerful greenhouse gas, more powerful a greenhouse gas than carbon dioxide. So when that went away, it got colder, and this may be the explanation of the most severe ice age that has ever happened in Earth's history, called the Huronian glaciation, which lasted from 2.4 to 2.1 billion years ago. So that was a major glaciation, and then later, considerably later, between 800 and 625 million years ago, there was another series of major glaciations called snowball Earth, when possibly the whole Earth came under ice, although people are now arguing that there's a stretch of tropical oceans that didn't freeze. The cause of that second one is unclear, but it shows that the Earth's climate has been erratic in those days. But luckily, the changes in climate were slow enough, and the rise of oxygen was slow enough that evolution could save the day. Organisms developed that could survive oxygen poisoning, and in fact even use oxygen. So animal cells actually learn how to metabolize oxygen. And around 540 million years ago, the first multicellular life arose, and some people argue that that's in response to these crises. So that's how life as we know it sort of got going. But since then, there have been 5 really big mass extinctions. They're called the Big Five, and they're these yellow triangles here. Don't worry too much about this graph, but this is a rough measure of how many different genuses or genera of organisms there are. So those are a larger grouping than species. And basically, biodiversity, as measured by the number of genera, has been increasing over time. But you'll notice that it wasn't a smooth increase at all. It was wiggling up and down, and you can say it like it was actually generally going down from 350 million years ago to 200 million years ago. So I'll talk about these 5 big mass extinction events, and but then there are others as well. So each one of them is a really interesting story, but I should say that for each one of them, we're having a lot of trouble, except for the last one. We're having a lot of trouble figuring out exactly what caused the mass extinction. And I watch a lot of crime shows, and I realize that it's a lot like that you see a dead body, and then the whole show is about like what caused that. It's much harder to figure out the cause of the extinction than to see the dead body. Or in this case, what you see is the absence of fossils of some particular kind above a certain strata. So you see like, oh, there's lots of these guys, and then they're gone. And then you have to guess what happened, which is hard. So the first one I want to talk about is called the Ordovician-Silurian extinction. It's at the transition between the Ordovician era and the Silurian era, 445 million years ago, so about 500 million years ago. 85% of marine species went extinct. That's enormous. This is a depiction of what the underwater near the shore might have looked like before that event. So you see these nice cephalopods, these nice, I'm sorry, I forget what these guys were called, sort of like sea anemones. And in the Ordovician, most of life was in the sea. So this is a major blow to life. So what happened? Well, it's known that there was a big phase of global cooling at this time, another big glacial cycle. And in fact, there's so much glaciation that sea levels are drastically lowered. So right now we're facing the opposite problem, right? That suddenly we're melting huge amounts of ice and sea levels are rising. But when you have ice ages, the reverse happens. And quite possibly a lot of life was living in the seawater near the shore. So as the water lowered, their habitat was destroyed. That's the best theory people have. Then later, as glaciers melted, there was a second pulse of extinctions, and that's more mysterious, but there's a lot of evidence that there was less oxygen in the water at that time. The cause of that is uncertain, but there's a lot of evidence that that's true. So this extinction impacted biodiversity to the extent that it took 5 million years for biodiversity to recover from it. Okay, then the late Devonian extinction. So this is 372 to 359 million years ago. Not as bad, but still big. 70% of marine species went extinct at this time. This is a considerably different era by now, but there was plants and animals living on land at this point, and this extinction seems to have only affected marine life as far as we know. And people suspect it was another bout of global cooling responsible. And there are also, again, shortages of oxygen in ocean bottom waters. There are a lot of extinctions connected to lack of oxygen in the water. And people aren't always sure about what the cause of that lowered oxygen would be. But basically that could be enough to kill off all oxygen-dependent species. And this extinction wasn't sudden. It happened in several waves over a long period lasting 25 million years. So it's somewhat mysterious. It's really fun to read about it. People know a lot of stuff, but the whole story is sort of murky. Coral reefs were killed off by this extinction, and they only fully recovered 120 million years later, which is amazing. The new corals that came later were a completely different type of organism than the old corals. So right now, we're killing off coral reefs worldwide due to ocean heating, and people are valiantly trying to move coral reefs northwards. But it's quite possible that the coral reefs will just die out, as they have done a couple of times before, like this. And I can't really predict it, but it's interesting that what happens is that in the long run, new organisms arise to fill that niche and start some new kind of coral reef. But that's a slow process. Now, the biggest mass extinction of all that we know of is this Permian-Triassic extinction, 250 million years ago. So 80% of marine species and 70% of land vertebrates went extinct in this one. So this is the worst of the lot as far as percentages of species going extinct. It took about 50 million years for life on land to fully recover its biodiversity. And it took 100 million years for marine life to recover from this. So before this extinction, the seabeds near China, as we can judge from the fossils, looked something sort of like this. So you see a nice diversity of things living on the seabed and things swimming around. This is a great book if you're interested in the Permian extinction by Michael Benton, When Life Nearly Died. So this is the upper Permian before the Permian-Triassic extinction. And then after the extinction, it looked like this. So just a few species of clam-like things are found after that. So it's just a wipeout. So what caused it? So the best we can guess is that it has something to do with the fact that during this time, there were huge and very long-lived volcanic eruptions in Siberia. There's something called the Siberian traps, which are geological formations due to lots of lava flow in Siberia. So it seems that what happened was that there was this enormous volcanism emitting a lot of carbon dioxide into the air, which would cause global warming, and also the depletion of oxygen, perhaps due to like the reaction of the new rock with the oxygen in the air. That's one way that oxygen gets used up. So it's hard to know exactly what caused it, but it's known that the amount of carbon dioxide in the air shot up from about 400 parts per million, which is where we are now, approximately, to 2,500 parts per million. So that's like ridiculous. It's like, we are not going to get anywhere near that, I hope, ourselves. One theory is that when it could be caused by a massive release of methane from stuff under the ocean. Under the ocean, especially in the northern latitudes, it's actually possible for methane to get caught in ice crystals. So believe it or not, underneath the ocean, like in the northern parts of the ocean, there's ice because the water pressure is high enough that it's actually able to compress water into a kind of solid. And methane molecules can get caught in these cages of ice, and these cages are called clathrates. And if you yank up some of this ice, you can actually light it on fire, and it will catch on fire as the methane is released from it. So there's a lot of carbon down there in the form of methane. And if it warms up enough so that ice destabilizes, it could release that methane. That's one theory of why you could get a sudden rise in carbon. I mean, methane turns to carbon dioxide after a while. So this slide is confusing because I say carbon dioxide and methane. Both of them cause global warming. Okay, so that's the big one, and we do have some evidence for what caused it, namely these volcanoes in Siberia. The next one is called the Triassic-Jurassic extinction, 200 million years ago, and 70% of marine and land species went extinct. So by the end of the Triassic, there were again reptiles on land and in sea, many of which had died in the previous extinction. But the extinction at the end of the Triassic destroyed most of these, and also the last of the large amphibians. So up to this point, there were some very large amphibians, like this guy, has a funny name, Mastodonsaurus. And he's 6 meters long, and he's an amphibian. Well, we don't have guys like that around anymore. Maybe just as clad, I don't know. But the amphibians lost their dominance at this time, and so did the reptiles. So there's some kinds of reptiles that if you're like a kid, you call them dinosaurs, and you can like buy a kit that has little toy dinosaurs. But not all of those things are actually technically dinosaurs. So all the ones before the Triassic-Jurassic extinction were, well, not all of them, but most of them were not what we now call dinosaurs. Other kinds of reptiles. And so this extinction opened up niches for what would become the dinosaurs of the Jurassic. No one is sure what caused this extinction, but there's a theory, which is namely that we know that this supercontinent, this enormous continent called Pangaea, began splitting at that time into two smaller continents, Laurasia, which you can see is sort of like Europe and Asia, and Gondwana, which you can see is sort of like North America is up there in Laurasia, South America, Africa, Australia, and Antarctica, and India would be part of Gondwana. So this splitting seems to have caused a lot of floods of lava in a certain area called the Central Atlantic Magmatic Province, basically where the splitting was occurring. And so again, we could have had a situation where a lot of lava would be causing a lot of release of carbon dioxide into the atmosphere and causing global warming. So that could be the response, the cause. Okay, last extinction for now is the fifth one. This is the one that people know the most about. This is the Cretaceous Tertiary extinction, 66 million years ago. 75% of marine and land species went extinct at this time. And this one we have a pretty good explanation of. This is the famous one that you hear about that killed off the dinosaurs. And it's probably due to an asteroid that hit the Gulf of Mexico near a place called Chicxulub. We have actually, we're able to see the crater using some nice imaging methods. So we can still see that crater underneath the dirt, underneath the Gulf of Mexico as well. It's right on the shore. And there's remnants of the collision all over the Earth, like bits of platinum released from the meteor exploding and bits of molten glass that have solidified all over the whole planet. So this crater is 10 kilometers across. Sorry, the asteroid was probably 10 kilometers across, and it hit with an energy of 100 trillion tons of TNT. So that's 2 million times larger than the largest man-made bomb, which is this 57 megaton atomic or hydrogen bomb that the Russians made, called the Tsar bomb. I don't know why the Soviets named the bomb after the Tsar. Yeah, I don't get it. But anyway, but that was puny compared to this. And even that, I should say, was puny compared to this. So how did the moon get formed? Believe it or not, the best theory for how the moon got formed right now is that actually a planet hit the Earth 4.53 billion years ago. And there's a lot of study of this question of how the moon was formed. That is, was it just there and it like got into orbit around the Earth, or something else? And the best evidence seems to be now that this planet called Theia collided with the Earth at this time, and it seems to work if you make this planet be a little bit bigger than Mars and in an orbit fairly similar to Earth, so it's moving fairly slow compared relative to us. And if you simulate that, as this woman Robin Canup has done, you find that 50 minutes after it hits, it looks like this. So a huge chunk of the Earth's surface has been sheared off, about half of it, and it's red hot, shot into the air. About 5 hours later, the iron core and most of the debris comes crashing back down onto the Earth. And the Earth's entire crust and outer mantle melts. A quarter of this planet is actually turned into vapor because of the intensity of all this. And then what would happen would be, after a day, there'd be a ring of debris orbiting the Earth, sort of like Saturn's moon. Different. And within a century, what would happen is that it would slowly collect and form the moon that we know and love. And the iron from this other planet would, because it's heavier, would sink down to the center of the Earth. So that is an amazingly dramatic event. Luckily, that was probably before there was any life on Earth at this time. So nobody suffered. So asteroid impacts are extremely dramatic, and it took a lot of work to convince paleontologists that the extinction that killed the dinosaurs was due to this event that occurred on one afternoon, namely this asteroid hitting the Earth. But now that's been really made clear, and so people like to think that they like that explanation because it's simple in a way. So they would like to explain other mass extinctions by means of asteroid impacts, but there's actually not much evidence that any of the other mass extinctions that I've talked about are due to asteroid impacts. There is evidence of other asteroid impacts, but they're not as big, and they might have caused smaller extinction events. Most of the extinctions seem to be connected to changes in the atmosphere, basically, or changes in the sea level, which are connected, as I said, because of global warming will melt the ice caps and rise the sea level. So things like that seem to be the main culprits, as far as we know. But this is a really tricky branch of science, putting together the clues. So there are lots of mysteries left with this whole subject. And I just want to mention two that are quite different in nature. So one is, how stable is the Earth's climate? We're testing that out right now, right? We're saying, like, okay, we'll take the Earth, we'll just start dumping huge amounts of carbon dioxide into the air. If you ask, like, what's the main thing that people are doing? If you ask, like, what's the most amount of mass that people are converting into something else, like concrete, or making lots of concrete, but no, the most mass that we're doing, the most mass processing that we're doing is burning carbon. So that's basically the defining feature of our civilization in terms of just like physical processes. So we're testing out what will happen when we heat up the Earth rapidly by carbon dioxide in the air. And there's a theory that maybe something bad might happen. And one possibility is that it's called the clathrate gun hypothesis. So as I mentioned, there's a lot of methane locked in seabeds. And it's known that these reserves of carbon are somewhere between 1,500 and 2,000 billion tons of carbon. That's a lot. That's a lot more, 3 to 4 times as much as the amount of carbon in all the rest of the biosphere. And methane is a really powerful greenhouse gas. It's 25 times more powerful a greenhouse gas than carbon dioxide, at least for the first century in which you emit it. The good thing about methane is that it reacts with things and goes away. So after a century, it starts going away, whereas carbon dioxide takes much longer. But you see that if we did something, or if previously something had done something that made the clathrates under the seabed release their methane, there'd be massive global warming due to methane in the air.
Should that 5,000 be a 500 from what you said?
No.
You said something should be 3 times.
Oh, I'm sorry. I was just wrong. This is right. I was an idiot. Okay, I can't divide
Okay,
it.
okay.
It's not 3 times as much. It's just, okay. It's less. Okay. Yes. Yeah, the numbers are there. Are right. I was just saying the wrong stuff. Okay, but it's still significant. Sorry. Thanks for catching that. So this is a rather busy and complicated graph. It's very interesting. You could talk about it for way too long. But what it is basically is a graph of the Earth's temperature as estimated in various ways over the last 66 million years ago. 66 million years ago, or 65 million years ago, is when that asteroid hit and the dinosaurs died out. So this is sort of the post-dinosaur climate. And very roughly speaking, what happened was that it got warmer and then it got colder. That's a summary of the weather over the last 66 million years ago. It's actually very interesting, right? So if you look at like the last 12 million years ago, you notice that the temperature is going down and it's also getting more and more jittery. Those wiggles, that scratchy look to this thing, those are the glaciers, the glacier cycles, or what you popularly call the ice ages. But it's also worth noting that in a grand historical perspective, we are living in a rather cold part of the history of the Earth. Please don't come away thinking, yay, global warming, it'll be great, it won't be so cold anymore. You might think that here in Edinburgh. I think that because I'm from Southern California. So, but the problem is not the temperatures, it's the rate of change of the temperature. So if it suddenly warms up to the temperature it was in the Eocene, then none of the species we have right now, including us, will be adapted to that new climate and we'll all be in serious trouble. So anyway, that's what's been going on recently. You'll notice all sorts of other interesting things. It got cold all of a sudden around then. That's when Antarctica first froze over. So before then, Antarctica had ferns and things on it. It was not so cold. You'll notice another strange thing. It actually thawed up for a while and then froze over again. Some people, no one is completely sure why it did all these things, but one thing that happened around here that makes a whole lot of sense in terms of explaining all this is that before around this time, Antarctica was actually connected to South America. So before then, water could not flow all the way around Antarctica. Whereas now, cold water flows around and around Antarctica and just stays there, and it can get very cold. So they think that that breaking of the land bridge between South America and Antarctica may have been what froze over Antarctica, and it may even be to some extent responsible for cooling the whole planet. Because once you get a continent that freezes over, it's white, and it reflects a lot more light, and so the whole planet doesn't absorb as much light, so it gets cooler. So maybe that's part of the explanation for this general cooling trend that we've been having until basically today, when we started dumping huge amounts of carbon dioxide into the air. Okay, but back here, it was hot. And this tiny little spike is amazing. So temperatures shot up 6 degrees Celsius. Remember, right now we're really worrying about, like, we're going to cause maybe 2 or 3 Celsius warming, and that will be disastrous for human civilization. But this is 6 degrees Celsius. It shot up in 20,000 years, which is really fast from a geological scale, although not as fast as we're warming things up now, by the way. And it stayed hot for about 200,000 years, and then it cooled down again. People are really fascinated by that because of its vague resemblance to what we're doing now. It's another time in the Earth's history when it suddenly got hot. And there were extinctions at that time, though not a mass extinction. Some people think that what happened was that due to the general warming, there was this clathrate gun, the sudden release of methane into the air, and then later on, plants absorbed the excess carbon in the atmosphere. There's evidence of huge amounts of seaweed in the Arctic Ocean, which was really not frozen at that time, helping suck down the carbon dioxide at that time. So that's an interesting issue there. Was that caused by some destabilization of the methane under the water? And could we cause something like that now? I mean, the good news is that now it's a lot colder than it was then. So maybe not. But in the past century, temperatures have been rising about 40 times faster than in that Paleocene, Eocene thermal maximum, that little spike I showed you. And luckily, we're starting from a much colder temperature. Methane is already starting to bubble up from the Arctic oceans faster and faster. People are just seeing all sorts of strange things going on, like in Siberia, there are these explosions where methane suddenly destabilizes and creates a big crater. And so far, the amount that's coming out is very small compared to the amount of carbon that we're deliberately, quote unquote, putting into the atmosphere by burning it. I mean, we're putting in 10 billion tons of carbon by burning it, as opposed to just about 12 million tons due to this methane release. But the methane release is increasing, so you have to worry. Here, there are places in Siberia where if you light a match, the methane will actually catch on fire because it's coming up there. So that's an example of one of many different puzzles that we're faced with now about what will happen to the Earth's climate when we do this massive experiment, this massive unplanned experiment. And then the really big question is, how will we respond to all of this? What will we do about the Anthropocene? Will we recognize that now we're in charge of the biosphere and we have to behave like we're grown-ups for a change and start dealing with the biosphere in the way you might like take care of a garden or something like that? Or not? We have not much time to stop some serious effects of global warming or some serious effects of habitat loss which is causing extinctions. So will we change our ways fast enough to survive? Maybe if we change our ways well enough, we'll even prosper. Because I think a lot of the changes we need to make could actually be beneficial, not just sacrifice. Another possibility is that our civilization will collapse, but humanity will still survive. There's a recent release from some insurance school, insurance department at Exeter, where they predict maybe if we keep on going the way we're going, the economy will lose half of its GDP by around 2070. So if the economy, and they said that would be an exceptionally challenging climate for investors. Yeah, so a civilizational collapse is something that insurance agents, they're not quite up to being able to make money in that type of situation. But so we could have various amounts of collapse. Collapse is a funny term when it comes to civilizations, because very often civilizations have collapsed, but people live on. So it's quite possible that something of that nature will happen, or that parts of the world will prosper and other parts will collapse. Or, of course, it's possible that we'll just keep on burning carbon merrily away and just sort of kill ourselves off, or potentially even kill ourselves off. And if so, I think what will happen is that we'll just basically make way for other species, just the way all sorts of species I've described went extinct throughout the course of the Earth's history. And nobody mourns them, really. Life goes on. And so I don't think anyone will be too upset if we all die out, because we won't be there. And whatever else is there, they'll just not be having to deal with it. So I really have no great predictive powers, so I can't tell which of these scenarios we're going to see. Of course, the good news is that we do have some control, some limited control about which of these scenarios we will pursue. And, well, make up your own mind. Okay, thanks, that's it.
Well, thank you very much for the wonderful lecture. I think I'm supposed to chair the Q&A as well. So, do you have some questions?
Questions or comments?
Yeah. Isn't the crucial thing that, as many people currently predict, that our population before very long will peak and start declining, possibly quite rapidly, and that if that happens over, say, the next few decades, that could reduce our carbon emissions and reduce the pressure that we're putting on the rest of the natural environment.
You might want to repeat the question for the recording.
Oh, okay, yeah. So the question was, could it be that as population peaks and then goes down that will reduce pressure on the natural environment and basically get out of the crisis that way. That will definitely play an important role. I think we would have to also deliberately not expand our usage of natural resources per capita while that is going on. Because if you notice, I mean, currently what's going on is that different people on the planet emit vastly different amounts of carbon. If you compare the average person on the planet to the average American, it's a factor of, I forget now, but it's a significant factor, I forget, a factor of 5 or something like that. If you compare average Americans to billionaires or millionaires, they've been doing studies recently about how much those rich people emit, and it's vastly different. As long as everyone wants to become a millionaire, you don't need to have too many people around to destroy the planet. That's the problem. That's one problem. So, but maybe if we combine a determination to reduce our carbon emissions together with a population leveling off or declining, the combination might work. I should add, though, that there's population changes happen rather slowly, and we're really very short of time in terms of like preventing, for example, a 2 degrees Celsius climate increase in temperature.
The question?
You showed that sharp spike,
Uh-huh.
PM. How
Yeah.
do we know that because it is?
These,
How do we know about it?
well, someone told me about it. That's how I know about it. The way people measure all these ancient temperatures is very interesting and very complicated, right? So there's no direct way to measure the temperature in the ancient past. In fact, nobody has any direct temperature measurements really since before around 1800. Luckily, the British Empire, one of the good things about it is they sent thermometers around the globe and made people measure the temperature all over the place. They're very systematic about such things. But so since then, we've actually known the temperature. These are measured in various types of ways, which are these obscure sidebar remarks here. So, for example, there's a correlation between temperature and how much oxygen 18 there is versus oxygen 16. So oxygen 16 is the normal kind of oxygen. Oxygen 18 is a heavier isotope of oxygen. And the heavier isotope of oxygen makes water that's a little more likely to freeze, because the water is actually a little heavier, and a little less likely to get into the air. And so there's reason to think that the concentration of oxygen 18 as measured in mud underneath the ocean floor is a way of estimating the temperature at the time when that mud was first laid down. So that's what you call a proxy for temperature. So there's and then there are others. There are many ways. So all of these are estimated in different kind of ways. And so it's a tricky business. And you could, if you wanted to be skeptical, you could have a lot of fun arguing with the climate scientists and the paleontologists who's come up with these different ways of measuring things. Of course, you try to get multiple ways of measuring things and see if they all match. But it's a really tricky business.
Well, I suppose commonsensically we observe effects of temperature even in ordinary life, right, without measuring them. And scientists make, I suppose, do refined versions of that.
Yeah, there are many different refined versions of that. So, for example, one sort of easy to understand one is that there's some kind of plants that thrive when it's cold and others that thrive when it's warm. And what they do in the more recent eras is they look at the pollen in the dirt from these different kind of plants. That works pretty well for like the last, I don't know what, 20,000 years or so, just looking at pollen. When you get back this old, the plants are all completely different, and so you can't really do it in quite such a way. Yeah.
And very crudely, if any of us look at a picture of some part of the world, we can probably have some guess of how hot or cold
Yeah,
it
that's,
is
yeah,
around
that's
here.
right. Yeah, certainly.
Yeah. Other questions? Yambo?
I was wondering if you're familiar with James Lovelock's findings.
Uh-huh.
I think he mentioned that 50 degrees Celsius is sort of the limit at which life can no longer survive.
That sounds like a good estimate to me. Yeah. Uh-huh.
How close do you think we are to reaching that average?
Well, we're pretty far from that. Sorry, I'm really bad at remembering things like what's the average temperature now, but I just luckily happen to have a chart of it here. So right now, the Earth just went up to 17 Celsius global mean temperature. And then if you go back in the past, you see that you see temperatures up to like 12 Celsius above what it is now are what we reached then. So that would be, I can't add very fast, but that, anyway, that's still well below 50 Celsius. I mean, so there's no chance that even back then that like life is going to completely die out due to the whole Earth being anywhere near 50 Celsius. Of course, there are places on the Earth now which get up to temperatures like that. But I don't think I don't think the extinction of life on Earth due to the whole Earth becoming so hot is the main thing to be thinking about right now. That is, there are lots of bad things that can happen that are much short of that. That are more sort of relevant to us, I think. Yeah.
I think you made the point that trying to solve a problem by extracting carbon dioxide from the air, particularly if you use energy created by burning carbon, is really not the way to proceed.
Yes.
And therefore, obviously, reducing our carbon emissions is the critical feature, if we're going to avert this crisis. Just one question. How much would you say that preserving and even expanding suitable types of vegetation can help in averting the crisis?
Yeah, so an interesting thing is that a forest that is more or less in equilibrium is not actually sucking down more carbon dioxide than it's emitting. So while existing forests, if you get rid of them, will emit a lot of carbon dioxide, partially because the soil will then start emitting carbon dioxide, and partially just because you've ripped up all these trees. So it's very important to prevent deforestation. It's not true that just like having a lot of forests that have always been there, still be there, those forests will not save the day by sucking down a lot more carbon dioxide. Planting new forests will suck down carbon dioxide for a while. People have found so far, unfortunately, that a whole lot of projects where people try to get carbon credits by saying, I promise to plant tons of trees and that will reduce carbon in the air by such and such. A whole bunch of those projects so far have been quite unsuccessful because what people tend to do is they plant a whole bunch of trees and then they don't pay much attention to them and then the trees die. So it takes work to create a forest in a place where there hadn't been a forest, and it takes deliberate long-term attention. There are other methods that I'm a little more optimistic about, actually. So, for example, one thing that we do right now is in agriculture, every year there are very roughly, I'm probably off, but like 6 billion tons of crop residue that people cart off and throw away. So just husks and all sorts of crud that you don't want to eat. So because agriculture is such an enormous project already, it has the potential to suck a lot of carbon dioxide from the air, and it's doing it, but a whole bunch of it is going into this crop residue that we then don't do anything intelligent with. We just throw it away. What does it do? It rots and it releases the carbon dioxide. If we could bury that stuff, that would be a way to suck out a lot of carbon dioxide from the air. And there are other methods as well that one can imagine. And an interesting feature of all of them, which is connected to what you're saying, is that all of them involve using plants. Because plants are basically solar-powered carbon dioxide extraction devices. So that's just exactly what you wish that you'd have, and that's what they are. And the only downside of them is the plants have no desire, quote unquote, to take that carbon and sequester it, bury it in a way that will stay sequestered. So we need to help them out if we want to harness their amazing ability to suck carbon dioxide from the air into some way to actually remove carbon dioxide from the air more or less permanently. But changing agriculture practices is one way to actually get a lot of that done.
Is what you said a moment ago an example of helping out, burying the
yeah, just bury. Yeah, I mean, it would be a major industrial undertaking. You'd have to pay people to do it because they don't want to do it, right? Nobody wants to take their crop residues and put it on a truck and take it over to some old salt mine or whatever and bury it. So, I mean, it requires, I believe, either some really smart economist or else government intervention to get this to happen. But at least it's thermodynamically working with the system instead of against the system, the way it would be if you're like just trying to build a machine to suck carbon dioxide from the air. Yeah.
So just a quick follow-up. What about things in the sea, like algae, seaweed, these sort of things?
Yeah, people are trying to do experiments on that. So one idea that people have is that if you add iron to the ocean, that more algae would grow there, because it turns out that algae in the ocean are limited by the iron concentration, interestingly. That's like the limiting nutrient. So you sprinkle a lot of iron-containing chemicals of the sort that plants can eat into the ocean, a whole bunch of algae grow, they eventually die, and here's the hard part. You hope that they fall to the bottom of the ocean and keep the carbon down there. So they've done some small-scale experiments like this, but they found that what happens is that as all this algae starts going down, all these sea creatures go like, yay, free food, and they eat all this algae, and the carbon seems to not be getting sequestered. So, but people should still do types of experiments like that.
Thank you.
Yes?
So why can't we recreate the Carboniferous?
The Carboniferous?
Yeah, in other words, it made all that coal was made
right.
naturally. What was happening then that we can't do now?
I think we are recreating the Carboniferous. We're making it extremely hot and putting lots of carbon dioxide into the air. We'll die out.
Oh, and
Then there will be lots of ferns and things growing.
Too late.
And they will die out and turn into coal and turn into oil. And then millions of years later, another civilization just like us can use that oil and start it all over again. That's one possibility, which it doesn't really solve anything. Another thing we can do, by the way, speaking of different possible solutions, it's a very interesting thing, is just put a bit of more dust up into the stratosphere, like put a bit of sulfur dioxide or nitrogen oxides up in sulfur dioxide into the atmosphere, reflect a bit of sunlight, and it will cool things down. I think people need to do experiments like that. There are already people thinking about it a lot. People are very nervous about this for apt reasons, and the usual reason is that we're playing God, we're controlling the climate. But the thing is, we're already playing God and controlling the climate. We're just playing like a really stupid God right now, who's like controlling the climate without thinking about what we're doing. It would be an enormous responsibility to be maintaining the climate by reflecting sunlight, because if people quit because they get into a war and no one wants to pay their bills or something like that, then all of a sudden the temperature would start shooting up. So I mean, you'd be basically, with things like this, you'd be sort of saying like, okay, I promise we're going to run the Earth from now on. But the interesting thing about it is that it doesn't take, it's a very cheap way of reducing the total amount of solar absorption. I mean, it's much cheaper economically than any of these other things that we've talked about. People are just nervous about it, and I think rightly so. But I sometimes think things are going to get so bad that at some point people are going to say, the heck with it, we're going to do this, because it's, in fact, even one country could go ahead and do this, and they might. I'm not saying that's good, but that might happen.
Yeah, I think we've had a lot of good questions and a lot of good proposals for what you could all go out and do, which the crises we're up against. And so we have some refreshments outside, and where you can ask more questions to John, at least for a little while before he gets hungry. So,
I can talk with one side of my mouth.
So maybe let's thank him again for this wonderful lecture.